Probability distribution essay. A probability distribution is a function that describes the likelihood of different outcomes in a random process. It is a fundamental concept in probability theory and statistics and plays a central role in many fields, including engineering, physics, economics, and finance. It is a fundamental concept in probability theory and statistics and plays a central role in many fields, including engineering, physics, economics, and finance. There are two main types of probability distributions, discrete and continuous. A discrete probability distribution describes the probabilities of outcomes that can take on only a finite or countably infinite number of values. For example, the probability distribution of rolling a six-sided die is a discrete distribution, as the outcome can only take on the values of 1, 2, 3, 4, 5, or 6. The distribution function for a discrete probability distribution is called a probability mass function PMF. On the other hand, a continuous probability distribution describes the probabilities of outcomes that can take on any value within a specified range. For example, the normal distribution is a continuous distribution that describes the probabilities of outcomes in a random process that is influenced by many independent factors. The distribution function for a continuous probability distribution is called a probability density function PDF. One of the most important properties of a probability distribution is its expected value, which is the average value of the outcomes weighted by their respective probabilities. The expected value is a measure of the central tendency of the distribution and is often used to make predictions about future outcomes. Another important property of a probability distribution is its variance, which measures the spread of the distribution around its expected value. In addition to the normal distribution, there are many other common probability distributions, including the binomial distribution, Poisson distribution, exponential distribution, and gamma distribution. Each of these distributions has its own set of properties and is suited for modeling different types of random processes. Overall, probability distributions are a fundamental tool for understanding and analyzing random processes. They allow us to make predictions about future outcomes and quantify the likelihood of different events occurring. As such, they are a key component of many fields, including finance, engineering, and physics, and are essential for making informed decisions in the face of uncertainty. Next topic. Binomial probability distribution explanation, steps, example and applications. The binomial probability distribution is a type of discrete probability distribution that models the number of successes in a fixed number of independent trials, where each trial has only two possible outcomes, success or failure. The distribution is called binomial because it is based on the binomial theorem, which states that the expansion of p plus q caret n, where p and q are the probabilities of success and failure, respectively, and n is the number of trials, gives the coefficients of a binomial probability distribution. The probability of exactly k successes in n independent trials, where the probability of success is p and the probability of failure is q equals 1p, can be calculated using the following formula. P x equals k equals n choose k asterisk p caret k asterisk q caret n k, where n choose k equals n. K, n k, is the binomial coefficient, which represents the number of ways to choose k items from a set of n items. To calculate the probability of a range of successes, such as Px is less than or equal to k, or Px is greater than or equal to k, we can use the cumulative distribution function, CDF, which adds up the probabilities of all possible outcomes up to or including k. Example, suppose we flip a fair coin 10 times and want to find the probability of getting exactly 4 heads. Using the binomial probability formula, we have Px equals 4 equals 10 choose 4 asterisk 0.5 caret 4 asterisk 0.5 caret 6 equals 0.205. Alternatively, we could use a binomial probability table or a binomial probability calculator to find the answer. Applications. The binomial probability distribution is commonly used in a variety of fields, including quality control. A manufacturer may use the binomial distribution to determine the probability of a certain number of defective items in a sample. Biology. Biologists may use the binomial distribution to model the probability of a certain number of mutations in a population. Finance. Investors may use the binomial distribution to model the probability of a stock price rising or falling over a certain period of time. Sports. Coaches may use the binomial distribution to model the probability of a team winning a certain number of games in a season. Overall, the binomial probability distribution is a useful tool for modeling situations with only two possible outcomes and can provide valuable insights into the likelihood of different events occurring. Next topic. Poisson probability distribution explanation, steps, example and applications. The Poisson probability distribution is a type of discrete probability distribution that models the number of events occurring in a fixed interval of time or space. It is named after French mathematician Siméon Denis Poisson, who introduced the distribution in the 19th century to model the number of errors made by a typesetter in a given length of printed text. The probability of observing exactly k events in a fixed interval of time or space, where the expected number of events is lambda, can be calculated using the following formula: Px equals k equals e caret lambda lambda caret k k, where e is the mathematical constant approximately equal to 2.71828. To calculate the probability of a range of events, such as Px is less than or equal to k, or Px is greater than or equal to k, we can use the cumulative distribution function, CDF, which adds up the probabilities of all possible outcomes up to or including k. Example, suppose that on average, a certain road has 2 accidents per day. What is the probability of having 4 accidents in a day? Using the Poisson probability formula, we have Px equals 4 equals e caret minus 2 asterisk 2 caret 4 4 equals 0.0902. Alternatively, we could use a Poisson probability table or a Poisson probability calculator to find the answer. Applications. The Poisson probability distribution is commonly used in a variety of fields, including manufacturing. Companies may use the Poisson distribution to model the number of defects in a certain number of products. Queuing theory. The Poisson distribution is used to model the arrival of customers at a service center, such as a call center or a hospital emergency room. Biology. Biologists may use the Poisson distribution to model the number of mutations in a certain length of DNA. Finance. Analysts may use the Poisson distribution to model the number of credit defaults in a portfolio of loans. Overall, the Poisson probability distribution is a useful tool for modeling situations where events occur randomly and independently over a fixed interval of time or space. It can provide valuable insights into the likelihood of different events occurring and help inform decision-making in a variety of fields. Next topic. Normal probability distribution explanation, steps, example and applications. The normal probability distribution, also known as the Gaussian distribution, is a continuous probability distribution that is widely used in statistics and probability theory. It is named after mathematician Carl Friedrich Gauss, who first described the distribution in the early 19th century. The normal distribution is characterized by two parameters, the mean mu and the standard deviation sigma. The probability density function PDF of the normal distribution is given by the following formula. Fx equals 1 sigma square root 2 pi e caret x mu squared 2 sigma caret 2. Where e is the mathematical constant approximately equal to 2.71828, pi is the mathematical constant approximately equal to 3.14159, and square root 2 pi is the square root of 2 pi. The normal distribution is a symmetric bell-shaped curve, with the mean at the center and the standard deviation determining the spread of the curve. The curve approaches zero on both ends but never touches the x-axis. To calculate probabilities for a normal distribution, we can use a table of standard normal probabilities, which gives the probabilities for a normal distribution with mean 0 and standard deviation 1. We can convert any normal distribution to a standard normal distribution by subtracting the mean and dividing by the standard deviation. Example, suppose that the weights of a certain population of apples are normally distributed with a mean of 150 grams and a standard deviation of 5 grams. What is the probability of selecting an apple at random that weighs between 140 and 155 grams? To solve this problem, we first standardize the distribution by subtracting the mean and dividing by the standard deviation. C equals 140,150, 5 equals 2. C equals 155,150, 5 equals 1. We then use a standard normal probability table or a calculator to find the probabilities. P minus 2 is less than or equal to Z is less than or equal to 1 equals P, Z is less than or equal to 1 P, Z is less than or equal to minus 2 equals 0.84130.0228 equals 0.8185. Alternatively, we could use the formula for the normal distribution with mu equals 150 and sigma equals 5 to calculate the probabilities directly. Applications. The normal distribution is used in a variety of fields, including quality control. Companies may use the normal distribution to model the distribution of product measurements and determine acceptable limits. Finance. Analysts may use the normal distribution to model the distribution of stock returns and calculate the probability of different investment outcomes. Psychology. Researchers may use the normal distribution to model the distribution of test scores and determine cutoffs for different performance levels. Epidemiology. Public health officials may use the normal distribution to model the distribution of a disease in a population and predict the likelihood of an outbreak. Overall, the normal distribution is a fundamental concept in statistics and probability theory and is widely used in a variety of applications. It provides a useful tool for modeling continuous data and making statistical inferences about populations. Next topic. Difference between parametric and non-parametric statistics essay. Parametric and non-parametric statistics are two types of statistical analyses used to analyze data in different ways. The main difference between these two types of analyses is the assumptions that are made about the underlying population distribution. Parametric statistics assume that the data are normally distributed or follow a known distribution, and that the parameters of the distribution, such as the mean and standard deviation, are known or can be estimated from the sample data. The methods of parametric statistics are often based on probability theory and use parametric models to describe the relationship between the variables. Non-parametric statistics, on the other hand, do not make any assumptions about the population distribution. Instead, they use methods that are based on ranks, medians, and other distribution-free measures to analyze the data. Non-parametric methods are often used when the data do not meet the assumptions of parametric statistics or when there is no prior knowledge about the underlying population distribution. Here are some key differences between parametric and non-parametric statistics. Assumptions. Parametric statistics require assumptions about the population distribution, while non-parametric statistics do not. Sample size. Parametric statistics generally require a larger sample size than non-parametric statistics to make reliable inferences. Statistical power. Parametric statistics have greater statistical power than non-parametric statistics, meaning that they are better able to detect significant differences between groups or variables. Data types. Parametric statistics are typically used for continuous data, while non-parametric statistics can be used for any type of data, including nominal and ordinal data. Complexity. Parametric statistics are more complex and require more advanced statistical knowledge than non-parametric statistics. Examples of parametric statistics include t-tests, ANOVA, linear regression, and logistic regression, while examples of non-parametric statistics include the Wilcoxon-Rank sum test, the Mann-Whitney U test, and the Kruskal-Wallis test. In general, the choice between parametric and non-parametric statistics depends on the nature of the data and the research question. If the data meet the assumptions of parametric statistics and the research question requires inference about population parameters, parametric statistics may be more appropriate. However, if the data are not normally distributed or the research question does not require inference about population parameters, non-parametric statistics may be more appropriate. Next topic. Testing of hypothesis essay with examples and importance in biostatistics. Hypothesis testing is a statistical method used to make decisions about a population parameter based on sample data. In hypothesis testing, we make an initial assumption about the population parameter, known as the null hypothesis H0, and then collect sample data to see if there is enough evidence to reject or fail to reject the null hypothesis. The general process of hypothesis testing involves the following steps: formulate the null hypothesis H0 and the alternative hypothesis HA. Collect sample data and calculate a test statistic. Determine the p-value, which is the probability of obtaining a test statistic is extreme or more extreme than the one calculated, assuming that the null hypothesis is true. Compare the p-value to the level of significance alpha, which is a predetermined threshold for rejecting the null hypothesis. Make a decision about whether to reject or fail to reject the null hypothesis based on the p-value and the level of significance. Here are some examples of hypothesis testing. Example 1. A pharmaceutical company claims that a new drug reduces cholesterol levels in patients. A clinical trial is conducted with a sample of 100 patients, and the mean cholesterol level is found to be 175 mg per deciliter with a standard deviation of 10 mg per deciliter. Test the hypothesis that the drug does reduce cholesterol levels with a 5% level of significance. Null hypothesis. The drug does not reduce cholesterol levels, mu equals 180. Alternative hypothesis. The drug does reduce cholesterol levels, mu less than 180. Test statistic. Z equals 175,180, 10 SQRT, 100 equals minus 2.5. P-value. P/Z less than minus 2.5 equals 0.0062. Decision. Since the p-value is less than the level of significance, 0.05, we reject the null hypothesis and conclude that the drug does reduce cholesterol levels. Example 2. A researcher wants to test the hypothesis that the mean height of adult males in a certain population is 70 inches. A sample of 50 men is selected, and their heights are measured. The sample mean height is found to be 69 inches with a standard deviation of 2 inches. Test the hypothesis at a 1% level of significance. Null hypothesis. The mean height of adult males is 70 inches, mu equals 70. Alternative hypothesis. The mean height of adult males is not 70 inches, mu does not equal 70. Test statistic. T equals 6972, SQRT, 50 equals minus 2.82. P-value. Pt greater than 2.82 equals 0.0074. Decision. Since the p-value is less than the level of significance, 0.01, we reject the null hypothesis and conclude that the mean height of adult males is not 70 inches. Importance of hypothesis testing in biostatistics. Hypothesis testing is an important tool in biostatistics because it allows researchers to make inferences about population parameters based on sample data. By testing hypotheses, we can determine whether an intervention or treatment has a statistically significant effect on a disease or health outcome, or whether there is a significant association between two variables. Hypothesis testing also helps to ensure that results are not due to chance and can be replicated in future studies. Overall, hypothesis testing is a fundamental part of biostatistical research and plays a critical role in the development of evidence-based medicine. Next topic. Errors biostatistics essay. In biostatistics, errors can occur in data collection, analysis, and interpretation. Understanding the types of errors that can occur is important for interpreting study results and making informed decisions. There are two main types of errors that can occur in statistical analysis, type 1 error and type 2 error. Type 1 error, also known as a false positive, occurs when we reject the null hypothesis when it is actually true. In other words, we conclude that there is a significant effect or difference when there isn't one. The probability of making a type 1 error is denoted by alpha, and is also referred to as the level of significance. A smaller alpha means a lower probability of making a type 1 error, but also increases the risk of making a type 2 error. Type 2 error, also known as a false negative, occurs when we fail to reject the null hypothesis when it is actually false. In other words, we conclude that there is no significant effect or difference when there is one. The probability of making a type 2 error is denoted by beta. The power of a statistical test is 1 beta, which is the probability of correctly rejecting the null hypothesis when it is false. A higher power means a lower probability of making a type 2 error, but also increases the risk of making a type 1 error. The following are examples of type 1 and type 2 errors in biostatistics. Example 1. A clinical trial is conducted to test a new drug for treating a disease. The null hypothesis is that the drug has no effect on the disease, and the alternative hypothesis is that the drug does have an effect. If the study concludes that the drug is effective when it is not, this would be a type 1 error. On the other hand, if the study concludes that the drug is not effective when it actually is, this would be a type 2 error. Example 2. A researcher is studying the association between smoking and lung cancer. The null hypothesis is that there is no association between smoking and lung cancer, and the alternative hypothesis is that there is an association. If the study concludes that there is an association when there isn't one, this would be a type 1 error. If the study concludes that there is no association when there actually is one, this would be a type 2 error. To minimize the risk of type 1 and type 2 errors, researchers can increase the sample size of their study, use a lower level of significance alpha, increase the power of their statistical test, and perform multiple tests to confirm their findings. Additionally, it is important to critically evaluate study results and consider the possibility of errors when interpreting study conclusions. In conclusion, understanding the types of errors that can occur in biostatistical analysis is important for interpreting study results and making informed decisions. By minimizing the risk of type 1 and type 2 errors, researchers can increase the validity and reliability of their findings. Next topic. Confidence interval, levels of significance, critical region explanation, example and importance in biostatistics. In biostatistics, confidence intervals, levels of significance, and critical regions are important concepts in hypothesis testing and statistical inference. A confidence interval is a range of values that is likely to contain the true population parameter with a certain level of confidence. It is calculated based on the sample data and the standard error of the estimate. The level of confidence is often set at 95% or 99%, but can vary depending on the study design and research question. For example, a 95% confidence interval for the mean weight of a certain species of bird could be 45 grams, 55 grams, indicating that we are 95% confident that the true population mean weight falls between these values. The level of significance, denoted by alpha, is the probability of making a type 1 error, rejecting the null hypothesis when it is true in hypothesis testing. It is usually set at 0.05 or 0.01, but can vary depending on the study design and research question. For example, if we set alpha equals 0.05 in a study investigating the effect of a new drug, we are saying that we are willing to accept a 5% chance of falsely rejecting the null hypothesis that the drug has no effect. The critical region is the set of values that would lead to the rejection of the null hypothesis in hypothesis testing. It is determined based on the level of significance and the distribution of the test statistic. For example, if we are testing the mean of a population using a t-test with alpha equals 0.05, the critical region would be the set of t-values that fall outside of the range determined by the t-distribution with the appropriate degrees of freedom. Here's an example of how these concepts might be used in biostatistics. A researcher is studying the effect of a new treatment for a certain medical condition. The null hypothesis is that the treatment has no effect, and the alternative hypothesis is that it does have an effect. The researcher conducts a randomized controlled trial with 100 participants and calculates the mean improvement in symptoms for the treatment group and the control group. The difference in means is 3 points on a scale of 0 to 10, with a standard error of 1.5 points. The researcher calculates a 95% confidence interval for the difference in means is 0.2, 5.8. This indicates that we are 95% confident that the true population difference in means falls between these values. The researcher also conducts a two-sided t-test with alpha equals 0.05 to test the null hypothesis. The calculated t-value is 2, which falls outside of the critical region determined by the t-distribution with 98 degrees of freedom. Therefore, the researcher rejects the null hypothesis and concludes that the treatment has a significant effect on symptom improvement. The importance of confidence intervals, levels of significance, and critical regions in biostatistics lies in their ability to help researchers make informed decisions based on data. By calculating confidence intervals and conducting hypothesis tests, researchers can determine the range of likely values for population parameters and make conclusions about the effectiveness of interventions or the presence of associations between variables. Additionally, understanding these concepts is important for critically evaluating study results and interpreting the validity and reliability of findings. Open sidebar. Normality test importance. Next topic. Normality test explanation and importance with example in biostatistics. Normality test, also known as a test for normal distribution, is a statistical test used to determine whether a given dataset follows a normal distribution or not. In other words, it checks whether the data is normally distributed or not. A normal distribution is a bell-shaped curve, where the majority of the data is centered around the mean, and the distribution is symmetric around the mean. Many statistical methods, such as t-tests and ANOVA, assume that the data is normally distributed, so normality tests are important to check the assumption before using these methods. There are several normality tests available, including the Shapiro-Wilk test, Anderson-Darling test, and Kolmogorov-Smirnov test. These tests compare the observed distribution to the theoretical normal distribution and provide a p-value, which indicates the likelihood of observing the data if it came from a normal distribution. If the p-value is less than the significance level, usually 0.05, we reject the null hypothesis that the data is normally distributed. In biostatistics, normality tests are commonly used to check the distribution of continuous data, such as age, height, and weight, before applying statistical methods to these data. For example, a researcher may want to test whether a new medication has an effect on blood pressure. Before applying a t-test to compare the mean blood pressure of the treatment and control groups, the researcher should check whether the blood pressure data is normally distributed using a normality test. If the data is not normally distributed, the researcher may need to use a non-parametric test instead of a t-test. Overall, normality tests are important to ensure that the assumptions of statistical methods are met and to make accurate statistical inferences from the data. Next topic. T-test test explanation, steps, example and importance with example in biostatistics. A t-test is a statistical test used to compare the means of two groups of data. It is a parametric test, which means that it assumes that the data is normally distributed and has equal variances. T-tests are commonly used in biostatistics to compare the means of two groups of patients, such as those who receive a new treatment and those who receive a placebo. Here are the steps to perform a t-test. Define the null hypothesis and alternative hypothesis. The null hypothesis H0 states that there is no significant difference between the means of the two groups, while the alternative hypothesis HOT states that there is a significant difference between the means of the two groups. Calculate the test statistic. The t-test statistic is calculated by dividing the difference between the means of the two groups by the standard error of the difference. The standard error of the difference takes into account the sample size, variance, and standard deviation of each group. Determine the degrees of freedom. The degrees of freedom df is calculated as the sum of the sample sizes of the two groups minus 2. Determine the critical value. The critical value is the value at which we reject the null hypothesis. It is determined by the significance level, usually 0.05, and the degrees of freedom. Compare the test statistic to the critical value. If the test statistic is greater than the critical value, we reject the null hypothesis and accept the alternative hypothesis. If the test statistic is less than the critical value, we fail to reject the null hypothesis. Here's an example of a t-test in biostatistics. A researcher wants to test whether a new drug reduces cholesterol levels in patients. The researcher recruits 50 patients and randomly assigns them to either the treatment group or the control group. The treatment group receives the new drug, while the control group receives a placebo. After 12 weeks, the researcher measures the cholesterol levels of both groups. The null hypothesis is that there is no significant difference in the mean cholesterol levels between the treatment group and the control group, while the alternative hypothesis is that the mean cholesterol levels in the treatment group are significantly lower than the mean cholesterol levels in the control group. The researcher calculates the t-test statistic and obtains a value of 2.36. The degrees of freedom are 48, 50 to 2. Using a significance level of 0.05, the critical value for a two-tailed t-test with 48 degrees of freedom is 2.01. Since the test statistic is greater than the critical value, the researcher rejects the null hypothesis and concludes that the new drug significantly reduces cholesterol levels in patients. Overall, t-tests are important in biostatistics because they allow researchers to determine whether there is a significant difference between the means of two groups of data. This information can be used to make important clinical decisions, such as whether to approve a new drug for widespread use. Next topic. Chi-square test explanation and steps. Example importance with example in biostatistics. The chi-square test is a statistical test used to determine whether there is a significant association between two categorical variables. It is a non-parametric test, which means that it makes no assumptions about the distribution of the data. Chi-square tests are commonly used in biostatistics to test for associations between diseases and risk factors. Here are the steps to perform a chi-square test. Define the null hypothesis and alternative hypothesis. The null hypothesis H0 states that there is no significant association between the two categorical variables, while the alternative hypothesis HOT states that there is a significant association between the two categorical variables. Create a contingency table. The contingency table shows the frequency of each category for each variable. It is a two-dimensional table with the rows representing one variable and the columns representing the other variable. Calculate the expected frequencies. The expected frequencies are the frequencies that would be expected if there was no association between the two variables. They are calculated by multiplying the row total by the column total and dividing by the grand total. Calculate the test statistic. The chi-square test statistic is calculated by summing the square differences between the observed frequencies and the expected frequencies, and then dividing by the expected frequencies. Determine the degrees of freedom. The degrees of freedom df is calculated as R1, C1, where R is the number of rows and C is the number of columns in the contingency table. Determine the critical value. The critical value is the value at which we reject the null hypothesis. It is determined by the significance level, usually 0.05, and the degrees of freedom. Compare the test statistic to the critical value. If the test statistic is greater than the critical value, we reject the null hypothesis and accept the alternative hypothesis. If the test statistic is less than the critical value, we fail to reject the null hypothesis. Here's an example of a chi-square test in biostatistics. A researcher wants to test whether smoking is associated with lung cancer. The researcher collects data from 200 patients, 100 of whom have lung cancer and 100 of whom do not have lung cancer. The researcher records whether each patient is a smoker or a non-smoker. The null hypothesis is that there is no significant association between smoking and lung cancer, while the alternative hypothesis is that smoking is significantly associated with lung cancer. The researcher creates a contingency table with two rows, smoker and non-smoker, and two columns, lung cancer and no lung cancer. The researcher calculates the expected frequencies by multiplying the row and column totals and dividing by the grand total. The researcher calculates the chi-square test statistic and obtains a value of 26.44. The degrees of freedom are 1, since there are two categories and two variables. Using a significance level of 0.05, the critical value for a chi-square test with 1 degree of freedom is 3.84. Since the test statistic is greater than the critical value, the researcher rejects the null hypothesis and concludes that smoking is significantly associated with lung cancer. Overall, chi-square tests are important in biostatistics because they allow researchers to determine whether there is a significant association between two categorical variables. This information can be used to identify risk factors for diseases and develop strategies for prevention and treatment. Next topic. F-test explanation and steps and example importance with example in biostatistics. The F-test is a statistical test used to compare the variances of two or more populations. It is a parametric test, which means it makes certain assumptions about the distribution of the data. In biostatistics, the F-test is commonly used to test for differences in variability between groups, such as in clinical trials or experiments. Here are the steps to perform an F-test. Define the null hypothesis and alternative hypothesis. The null hypothesis H0 states that the variances of the populations are equal, while the alternative hypothesis HOT states that the variances are not equal. Collect data from the populations. The data should be collected from at least 2 populations. Calculate the sample variances. Calculate the sample variances for each population. Calculate the F-test statistic. The F-test statistic is the ratio of the larger variance to the smaller variance. Determine the degrees of freedom. The degrees of freedom depend on the number of populations and the number of observations in each population. Determine the critical value. The critical value is the value at which we reject the null hypothesis. It is determined by the significance level, usually 0.05, and the degrees of freedom. Compare the test statistic to the critical value. If the test statistic is greater than the critical value, we reject the null hypothesis and accept the alternative hypothesis. If the test statistic is less than the critical value, we fail to reject the null hypothesis. Here's an example of an F-test in biostatistics. A researcher wants to compare the variability of the blood pressure readings from 3 different treatments. The researcher collects data from 10 patients for each treatment and calculates the sample variances as follows. Treatment A, 12.5, treatment B, 14.3, treatment C, 9.8. The null hypothesis is that the variances of the 3 treatments are equal, while the alternative hypothesis is that at least one of the variances is different. The F-test statistic is calculated as the ratio of the largest variance to the smallest variance. F equals 14.3, 9.8 equals 1.459. The degrees of freedom for the numerator are 2 and for the denominator are 27, n1, where n is the total number of observations. Using a significance level of 0.05, the critical value for an F-test with 2 and 27 degrees of freedom is 3.34. Since the test statistic is less than the critical value, the researcher fails to reject the null hypothesis and concludes that there is no significant difference in the variability of the blood pressure readings between the 3 treatments. Overall, F-tests are important in biostatistics because they allow researchers to compare the variability of 2 or more populations. This information can be used to determine whether there are significant differences between groups and to guide decisions about treatment or intervention strategies. Next topic. ANOVA test explanation steps example in importance with example in biostatistics. ANOVA analysis of variance is a statistical test used to determine whether there are significant differences between the means of 2. ANOVA analysis of variance is a statistical test used to determine whether there are significant differences between the means of 2 or more populations. In biostatistics, ANOVA is commonly used to compare the effectiveness of different treatments or interventions. Here are the steps to perform an ANOVA. Define the null hypothesis and alternative hypothesis. The null hypothesis H0 states that the means of all populations are equal, while the alternative hypothesis HOT states that at least one population mean is different. Collect data from the populations. The data should be collected from at least 2 populations. Calculate the sample means. Calculate the sample means for each population. Calculate the sum of squares. Calculate the sum of squares within groups SSW and the sum of squares between groups SSB. Calculate the F-test statistic. The F-test statistic is the ratio of the between-group variability to the within-group variability. Determine the degrees of freedom. The degrees of freedom depend on the number of populations and the number of observations in each population. Determine the critical value. The critical value is the value at which we reject the null hypothesis. It is determined by the significance level, usually 0.05, and the degrees of freedom. Compare the test statistic to the critical value. If the test statistic is greater than the critical value, we reject the null hypothesis and accept the alternative hypothesis. If the test statistic is less than the critical value, we fail to reject the null hypothesis. Here's an example of an ANOVA in biostatistics. A researcher wants to compare the effectiveness of 3 different drugs in reducing blood pressure. The researcher randomly assigns 10 patients to each drug and measures their blood pressure after 1 week of treatment. The data is summarized in the following table. Drug A, drug B, drug C. 100. The null hypothesis is that the means of the blood pressure readings for the 3 drugs are equal, while the alternative hypothesis is that at least one of the means is different. The sample means for the 3 drugs are: drug A, 135.3, drug B, 139.5, drug C, 130.7. The sum of squares within groups SSW is 106.67 and the sum of squares between groups SSB is 173.33. The F-test statistic is calculated as F equals SSB K1 SSW and K equals 173.33 to 106.67, 27 equals 5.12. Using a significance level of 0.05, the critical value for an F-test with 2 and 27 degrees of freedom is 3.34. Since the test statistic is greater than the critical value, the researcher rejects the null hypothesis and concludes that there is a significant difference in the effectiveness of the 3 drugs in reducing blood pressure. Overall, ANOVA tests are important in biostatistics because they allow researchers to compare the means of 2 or more populations. Next topic. Applications and advantages of t-test, chi-square, F-test, ANOVA. The t-test, chi-square test, F-test, and ANOVA are commonly used statistical tests in biostatistics with various applications and advantages. Applications and advantages of the t-test. The t-test is widely used to compare the means of 2 populations, such as comparing the effectiveness of 2 drugs with a difference in mean blood pressure before and after a treatment. The advantages of the t-test include its simplicity and applicability to small sample sizes. It can also be used to assess the statistical significance of differences in means between 2 groups. Applications and advantages of the chi-square test. The chi-square test is used to assess the association between 2 categorical variables, such as smoking status and lung cancer incidence. It can also be used to test goodness of fit, which is useful in determining whether a particular distribution fits the observed data. The advantages of the chi-square test include its flexibility and robustness, which means that it can handle a wide range of data types and distributions. Applications and advantages of the F-test. The F-test is used to compare the variances or standard deviations of 2 or more populations, such as comparing the variability of blood pressure readings between 2 different treatments. The advantages of the F-test include its flexibility and ability to handle data with unequal sample sizes. It is also a powerful tool for detecting differences and variances between groups. Applications and advantages of ANOVA. ANOVA is used to compare the means of two or more populations, such as comparing the effectiveness of different drugs in reducing blood pressure. The advantages of ANOVA include its ability to handle multiple groups and compare the means of more than two populations simultaneously. It is also a useful tool for detecting differences in means between groups and can handle data with unequal sample sizes. Overall, these statistical tests have a wide range of applications in biostatistics and can help researchers draw valid conclusions from their data. Understanding the advantages and limitations of each test can help researchers choose the appropriate test for their analysis and ensure the validity of their findings. Open sidebar. Kruskal-Wallis test explanation. Next topic. Kruskal-Wallis explanation steps example and importance. Kruskal-Wallis is a non-parametric statistical test that is used to compare three or more independent groups to determine if there are differences in their median values. It is an extension of the Mann-Whitney U test for two independent groups. Here are the steps for performing the Kruskal-Wallis test. State the null and alternative hypotheses. The null hypothesis is that there is no difference between the median values of the groups, and the alternative hypothesis is that at least one group has a different median value than the others. Rank the data. Rank all the observations from all groups together, regardless of which group they belong to. Calculate the test statistic. The test statistic is calculated by summing the squared rank deviations for each group, and then dividing by a factor that adjusts for the sample size and number of groups. This results in a chi-squared distribution with degrees of freedom equal to the number of groups minus 1. Determine the p-value. The p-value is the probability of observing a test statistic as extreme as the one calculated from the data, assuming the null hypothesis is true. This can be obtained from a chi-squared distribution table or calculator. Make a decision. If the p-value is less than the chosen significance level, e.g., 0.05, then we reject the null hypothesis and conclude that there is a difference in the median values of at least one group. Example, suppose we want to compare the heights of three different plant species A, B, and C. We measure the height of 10 plants from each species and obtain the following data. Species A, 12, 15, 18. We first rank all the data together, giving ties the average of their ranks. Then we calculate the test statistic using the formula, which gives us a chi-squared value of 8.03. Looking up the p-value from the chi-squared distribution table with 2 degrees of freedom, 3 groups 1, we get a value of 0.018. Since the p-value is less than 0.05, we reject the null hypothesis and conclude that there is a significant difference in the median heights of at least one plant species. Importance. The Kruskal-Wallis test is a valuable tool in data analysis when the assumptions of parametric tests, such as ANOVA, are not met. It is particularly useful when the data are not normally distributed or when there are outliers. By using the Kruskal-Wallis test, we can determine whether there are significant differences between groups, which can inform decisions and actions based on the results. Next topic. Mann-Whitney explanation steps example and importance. The Mann-Whitney U test is a non-parametric statistical test that is used to compare two independent groups to determine if there is a difference in their median values. It is also known as the Wilcoxon rank sum test. Here are the steps for performing the Mann-Whitney U test. State the null and alternative hypotheses. The null hypothesis is that there is. Here are the steps for performing the Mann. It is also known as the Wilcoxon rank sum test. Here are the steps for performing the Mann-Whitney U test. State the null and alternative hypotheses. The null hypothesis is that there is no difference between the median values of the two groups, and the alternative hypothesis is that the median value of one group is greater than the other. Rank the data. Rank all the observations from both groups together, regardless of which group they belong to. Calculate the test statistic. The test statistic is calculated by summing the ranks of the observations in one group and comparing it to the sum of the ranks in the other group. This results in a U statistic that can be compared to a table of critical values to determine if the difference is statistically significant. Determine the p-value. The p-value is the probability of observing a U statistic as extreme as the one calculated from the data, assuming the null hypothesis is true. This can be obtained from a table of critical values or a calculator. Make a decision. If the p-value is less than the chosen significance level, e.g., 0.05, then we reject the null hypothesis and conclude that there is a difference in the median values of the two groups. Example, suppose we want to compare the heights of two different plant species A and B. We measure the height of 8 plants from species A and 10 plants from species B and obtain the following data. Species A, 12, 15, 18, 20, 22, 24, 25, 28. Species B, 11, 13, 16, 19, 21, 23, 26, 29, 32, 36. We first rank all the data together, giving ties the average of their ranks. Then we calculate the U statistic using the formula, which gives us a value of 12.5. Looking up the p-value from a table of critical values for U, we get a value of 0.051. Since the p-value is greater than 0.05, we fail to reject the null hypothesis and conclude that there is no significant difference in the median heights of the two plant species. Importance. The Mann-Whitney U test is a valuable tool in data analysis when the assumptions of parametric tests, such as the t-test, are not met. It is particularly useful when the data are not normally distributed or when there are outliers. By using the Mann-Whitney U test, we can determine whether there are significant differences between two groups, which can inform decisions and actions based on the results. It is widely used in various fields, such as biology, medicine, and social sciences. Next topic. Applications of Kruskal-Wallis and Mann-Whitney. The Kruskal-Wallis test and the Mann-Whitney U test are both non-parametric tests that can be used in various applications when the assumptions of parametric tests are not met. Here are some specific examples of their applications. Kruskal-Wallis test. Comparing the performance of different treatments. The Kruskal-Wallis test can be used to compare the performance of different treatments or interventions on a response variable, such as the effectiveness of different medications on a disease. Analyzing survey data. The Kruskal-Wallis test can be used to analyze survey data where respondents rate their satisfaction with different products or services across multiple groups. Comparing groups with non-normal distributions. The Kruskal-Wallis test can be used to compare groups when the data are not normally distributed, such as in the case of skewed or highly variable data. Mann-Whitney U test. Comparing two independent groups. The Mann-Whitney U test can be used to compare the medians of two independent groups when the data do not meet the assumptions of parametric tests, such as in the case of non-normal distributions. Analyzing ordinal data. The Mann-Whitney U test can be used to analyze ordinal data, such as in the case of Likert scale survey responses or rankings. Testing for differerences in central tendencies. The Mann-Whitney test can be used to test for differences in central tendencies, such as comparing the median income of two different populations. Overall, both the Kruskal-Wallis test and the Mann-Whitney test are useful tools for analyzing data in situations where parametric tests are not appropriate or assumptions are not met. They provide a way to test hypotheses and draw conclusions about differences or similarities between groups, and can be applied in various fields such as healthcare, social sciences, and business. Next topic. Types of correlation essay. Correlation is a statistical method that measures the strength and direction of the relationship between two variables. Correlation analysis is widely used in many fields, including social sciences, engineering, finance, and healthcare, to name a few. There are several types of correlation that can be used depending on the nature and level of measurement of the variables involved. In this essay, I will describe 4 common types of correlation: Pearson correlation, Spearman correlation, Kendall correlation, and point biserial correlation. Pearson correlation. The Pearson correlation, also known as the product moment correlation, measures the linear relationship between two continuous variables. It is the most common type of correlation used in statistical analysis. Pearson correlation ranges from -1 to 1, where -1 indicates a perfect negative correlation, 0 indicates no correlation, and 1 indicates a perfect positive correlation. Pearson correlation assumes that the variables are normally distributed and that the relationship between them is linear. Spearman correlation. The Spearman correlation measures the monotonic relationship between two continuous or ordinal variables. Unlike Pearson correlation, it does not assume a linear relationship between the variables. Instead, it measures the degree to which the variables increase or decrease together. Spearman correlation ranges from -1 to 1, where -1 indicates a perfect negative monotonic correlation, 0 indicates no correlation, and 1 indicates a perfect positive monotonic correlation. Kendall correlation. The Kendall correlation, also known as Kendall-Stowe, is another measure of the monotonic relationship between two continuous or ordinal variables. Like Spearman correlation, it does not assume a linear relationship between the variables. Kendall correlation ranges from -1 to 1, where -1 indicates a perfect negative monotonic correlation, 0 indicates no correlation, and 1 indicates a perfect positive monotonic correlation. Kendall correlation is more robust than Spearman correlation for small sample sizes. Point biserial correlation. The point biserial correlation measures the relationship between a continuous variable and a dichotomous variable. It is commonly used in educational and psychological research to measure the correlation between a test score and a pass-fail outcome. Point biserial correlation ranges from -1 to 1, where -1 indicates a perfect negative correlation, 0 indicates no correlation, and 1 indicates a perfect positive correlation. In conclusion, correlation analysis is a valuable tool in statistical analysis that can help to uncover relationships between variables. The choice of correlation measure depends on the nature and level of measurement of the variables involved. The 4 types of correlation described above, Pearson correlation, Spearman correlation, Kendall correlation, and point biserial correlation, are the most commonly used measures of correlation in statistical analysis. By understanding these types of correlation, researchers can make informed decisions about which measure to use in their analysis. Next topic. Methods to measure correlation essay and scatter diagram explanation and importance. Correlation is a statistical technique used to measure the strength and direction of the relationship between two variables. There are several methods to measure correlation, including Pearson correlation, Spearman correlation, and Kendall correlation. In this essay, I will explain these methods of measuring correlation, as well as the importance of scatter diagrams in correlation analysis. Pearson correlation. Pearson correlation, also known as the product moment correlation, is the most commonly used method for measuring correlation. It is used to measure the linear relationship between two continuous variables. The Pearson correlation coefficient, denoted as R, ranges from -1 to +1, where a correlation coefficient of +1 indicates a perfect positive correlation, a correlation coefficient of -1 indicates a perfect negative correlation, and a correlation coefficient of 0 indicates no correlation. Pearson correlation is appropriate when both variables are normally distributed and have a linear relationship. Spearman correlation. Spearman correlation is a non-parametric method used to measure the relationship between two continuous or ordinal variables. Unlike Pearson correlation, Spearman correlation does not assume a linear relationship between the variables. The Spearman correlation coefficient, denoted as ρ, ranges from -1 to +1, where a correlation coefficient of +1 indicates a perfect positive monotonic correlation, a correlation coefficient of -1 indicates a perfect negative monotonic correlation, and a correlation coefficient of 0 indicates no correlation. Spearman correlation is appropriate when the variables are not normally distributed or when the relationship between the variables is nonlinear. Kendall correlation. Kendall correlation is another non-parametric method used to measure the relationship between two continuous or ordinal variables. It is similar to Spearman correlation but is more robust when the sample size is small. The Kendall correlation coefficient, denoted as tau, ranges from -1 to +1, where a correlation coefficient of +1 indicates a perfect positive monotonic correlation, a correlation coefficient of -1 indicates a perfect negative monotonic correlation, and a correlation coefficient of 0 indicates no correlation. Scatter diagrams are an important tool in correlation analysis. A scatter diagram is a graph that displays the relationship between two variables. The x-axis represents the independent variable, while the y-axis represents the dependent variable. Each point on the graph represents a pair of values for the two variables. Scatter diagrams can help to visualize the strength and direction of the relationship between the variables. In addition, they can help to identify outliers or unusual observations that may affect the correlation coefficient. Scatter diagrams are also useful for identifying nonlinear relationships between variables, which may be better represented by a non-parametric correlation method such as Spearman or Kendall correlation. In conclusion, correlation analysis is an important statistical technique used to measure the strength and direction of the relationship between two variables. Pearson correlation, Spearman correlation, and Kendall correlation are 3 commonly used methods for measuring correlation. Scatter diagrams are an important tool in correlation analysis, as they help to visualize the relationship between variables and identify outliers or unusual observations. By understanding these methods of measuring correlation and the importance of scatter diagrams, researchers can gain valuable insights into the relationships between variables. Next topic. Carl Pearson's coefficient of correlation essay with example. Carl Pearson's coefficient of correlation, also known as Pearson correlation or Pearson's R, is a statistical method used to measure the strength and direction of the linear relationship between two continuous variables. It was developed by the British mathematician Carl Pearson in the late 19th century and is the most commonly used method for measuring correlation. Pearson's coefficient of correlation is calculated as the covariance between the two variables divided by the product of their standard deviations. The formula for Pearson's R is R equals sigma xy, sigma x, sigma y, n sqrt, sigma x squared, n sqrt. X and Y are the two variables being measured. Sigma xy is the sum of the products of x and y. Sigma x and sigma y are the sums of x and y, respectively. Sigma x squared and sigma y squared are the sums of the squares of x and y, respectively, and is the sample size. Pearson's R ranges from -1 to +1, where a correlation coefficient of +1 indicates a perfect positive correlation, a correlation coefficient of -1 indicates a perfect negative correlation, and a correlation coefficient of 0 indicates no correlation. For example, suppose a researcher is interested in studying the relationship between the number of hours studied and the score obtained in a math exam. The researcher collects data from a sample of 30 students and calculates the Pearson's correlation coefficient as 0.75. This indicates a positive correlation between the two variables, with a strength of 0.75. Interpreting Pearson's R requires considering the magnitude and direction of the coefficient. A coefficient close to +1 or -1 indicates a strong correlation, while a coefficient close to 0 indicates a weak correlation. A positive coefficient indicates a positive correlation, meaning that as one variable increases, the other variable also tends to increase. A negative coefficient indicates a negative correlation, meaning that as one variable increases, the other variable tends to decrease. Pearson's R is widely used in many fields, including social sciences, economics, and psychology. It can be used to examine relationships between variables such as income and education, job satisfaction and productivity, and health behaviors and outcomes. It is also useful in predictive modeling, where the correlation between predictor and outcome variables is used to make predictions. In conclusion, Pearson's coefficient of correlation is a widely used statistical method that measures the strength and direction of the linear relationship between two continuous variables. It is a useful tool for understanding the relationships between variables and making predictions. Understanding how to calculate and interpret Pearson's R is an essential skill for researchers and analysts in many fields. Next topic. Spearman's correlation essay with example. Spearman's rank correlation coefficient, also known as Spearman's rho, is a statistical method used to measure the strength and direction of the relationship between two variables. It was developed by the British statistician Charles Spearman in 1904 and is used when the variables being measured are ordinal or ranked. Spearman's rho is calculated by first ranking each variable in order, from lowest to highest. The difference between the ranks for each pair of observations is then calculated. The formula for Spearman's rho is rho equals 1/6 sigma d squared n caret 2 to 1, where d is the difference between the ranks of the paired observations. Sigma d squared is the sum of the squared differences between the ranks and is the sample size. Spearman's rho ranges from -1 to +1, where a correlation coefficient of +1 indicates a perfect positive correlation, a correlation coefficient of -1 indicates a perfect negative correlation, and a correlation coefficient of 0 indicates no correlation. For example, suppose a researcher is interested in studying the relationship between the rank of education level and income level. The researcher collects data from a sample of 50 individuals and ranks their education levels and income levels from lowest to highest. The researcher calculates Spearman's rho as 0.70, indicating a strong positive correlation between education level and income level. Interpreting Spearman's rho requires considering the magnitude and direction of the coefficient, similar to interpreting Pearson's R. Regression analysis is a statistical technique used to explore the relationship between a dependent variable and one or more independent variables. There are several types of regression analysis, including linear regression. Linear regression is the most commonly used type of regression analysis. It is used to examine the relationship between a dependent variable and one or more independent variables, assuming a linear relationship between them. The goal of linear regression is to find the best fit line that describes the relationship between the variables. Multiple regression. Multiple regression is a type of regression analysis that examines the relationship between a dependent variable and two or more independent variables. Multiple regression is used when there are multiple factors that influence the dependent variable. Logistic regression. Logistic regression is a type of regression analysis used when the dependent variable is dichotomous binary in nature. Logistic regression is used to predict the likelihood of a binary outcome based on one or more independent variables. Polynomial regression. Polynomial regression is a type of regression analysis used when the relationship between the dependent variable and independent variables is nonlinear. Polynomial regression uses higher order polynomials to fit the data. Ridge regression. Ridge regression is a type of regression analysis used when there are multicollinearity issues in the data. Multicollinearity is a situation where two or more independent variables are highly correlated with each other, making it difficult to estimate their individual effects on the dependent variable. Ridge regression adds a penalty term to the least squares method to overcome the multicollinearity issue. Lasso regression. Lasso regression is similar to ridge regression, but it adds an additional penalty term to the least squares method that shrinks some of the regression coefficients to 0. Lasso regression is used for variable selection and can help to identify the most important independent variables. Poisson regression. Poisson regression is a type of regression analysis used when the dependent variable is a count variable. Poisson regression assumes that the dependent variable follows a Poisson distribution. In conclusion, regression analysis is a powerful statistical technique used to explore the relationship between a dependent variable and one or more independent variables. Understanding the different types of regression analysis can help researchers and analysts choose the appropriate technique for their research question and data. Next topic. Correlation and regression in simple terms. Correlation and regression are two statistical techniques used to study the relationship between two or more variables. Correlation measures the strength and direction of the relationship between two variables, while regression helps to predict the value of one variable based on the value of another variable. Correlation measures the degree of association between two variables. A correlation coefficient can range from -1 to 1, with -1 indicating a perfect negative correlation, 0 indicating no correlation, and 1 indicating a perfect positive correlation. A positive correlation means that as one variable increases, the other variable tends to increase as well, while a negative correlation means that as one variable increases, the other variable tends to decrease. Regression, on the other hand, is a technique used to model the relationship between two or more variables. In simple linear regression, a straight line is fitted to the data to predict the value of the dependent variable based on the value of the independent variable. In multiple regression, more than one independent variable is used to predict the value of the dependent variable. Regression is used to make predictions about the value of one variable based on the value of another variable. For example, a researcher might use regression to predict a person's income based on their level of education. In this case, education would be the independent variable and income would be the dependent variable. In summary, correlation measures the strength and direction of the relationship between two variables, while regression helps to predict the value of one variable based on the value of another variable. Both techniques are important tools for analyzing data and making predictions in a variety of fields, including business, social science, and engineering. Next topic. Regression equations. A regression equation is a mathematical formula that describes the relationship between a dependent variable and one or more independent variables. The equation is typically expressed as y equals a plus bx, where y is the dependent variable, x is the independent variable, a is the intercept or constant, and b is the slope or coefficient. In a simple linear regression equation, there is only one independent variable, and the equation takes the form y equals a plus bx, where y is the dependent variable, x is the independent variable, a is the intercept or constant, and b is the slope or coefficient. The intercept represents the value of the dependent variable when the independent variable is equal to 0. The slope represents the change in the dependent variable for each unit change in the independent variable. For example, suppose we are studying the relationship between a person's weight, dependent variable, and their height, independent variable. We collect data from a sample of individuals and use regression analysis to determine the relationship between the two variables. The resulting regression equation might be weight equals 100 plus 5.5 asterisk height. In this equation, the intercept is 100, which means that a person with a height of 0 would be expected to weigh 100 pounds. The slope is 5.5, which means that for each inch increase in height, we would expect a person's weight to increase by 5.5 pounds. Multiple regression equations involve more than one independent variable, and take the form y equals a plus b1 x1 plus b2 x2 plus bn xn, where y is the dependent variable, x1, x2, xn are the independent variables, a is the intercept or constant, and b1, b2, bn are the slopes or coefficients for each independent variable. In summary, a regression equation is a mathematical formula that describes the relationship between a dependent variable and one or more independent variables. It is a useful tool for making predictions and understanding the relationship between variables in a dataset. Next topic. Difference between regression and correlation analysis essay with example. Regression and correlation are two statistical techniques that are used to analyze the relationship between two or more variables. While both techniques are related and often used together, there are key differences between them. Correlation measures the strength and direction of the relationship between two variables. It tells us whether two variables are related and how strong that relationship is. Correlation coefficients range from -1 to 1, with values closer to -1 or 1 indicating a stronger correlation. A value of 0 indicates no correlation between the variables. Regression, on the other hand, is a method of modeling the relationship between two or more variables. It allows us to predict the value of one variable based on the value of one or more other variables. In regression analysis, we use one or more independent variables to predict the value of a dependent variable. For example, let's consider a study of the relationship between a person's age and their income. We might collect data on the age and income of a sample of individuals, and then use correlation analysis to determine whether there is a relationship between the two variables. If we find that there is a positive correlation between age and income, we know that as a person's age increases, their income tends to increase as well. However, correlation analysis does not tell us anything about the cause and effect relationship between age and income. It is possible that there is another variable, such as education or work experience, that is responsible for the observed correlation. To investigate further, we might use regression analysis to model the relationship between age and income, while controlling for other variables that could be affecting the relationship. In this case, we might include education and work experience as independent variables in our regression model. This would allow us to predict a person's income based on their age, education, and work experience. In summary, correlation analysis tells us whether two variables are related and how strong that relationship is, while regression analysis allows us to model the relationship between variables and predict the value of one variable based on the value of another variable. Both techniques are important tools for understanding the relationships between variables and making predictions in a variety of fields, including business, social science, and engineering.